This video is going to go through Chapter 12, Section 4, seemingly everybody's favorite topic, money, the mathematics of finance. Now again, interest can be your friend if you're saving. It can be your foe if you're borrowing. You guys going off to college? Sorry, I got some bad news about that. All right, so let's talk about, oh my goodness, you are what, juniors, maybe sophomores in high school? Let's talk about your retirement account. An annuity here is a way of saving money, earning interest, so that you can spend it later. Okay. Um, so as they define it, it's money that you pay in regular intervals. Could be annual, semi-annually, quarterly, monthly. Sometimes you'll have it taken out of every single paycheck. Payments usually made at the end of an interval, so that's an interesting thing you got to pay attention to here as we go through and look at some of these charts and diagrams and how things are calculated. When they use the phrase amount of an annuity, that's the sum of all of those payments that you've put in there and all of the interest that's been added. So A sub F is the final amount. So straight to example number one, suppose that you're able to scrape together $400 that you're going to deposit in an annuity twice a year, December 15th and June 15th. And you're going to keep this up for 10 years. And miraculously, somehow, you found somebody that's going to pay you 8% per year. We need to know something else because you're depositing just twice a year. Let's just keep that consistent. Your interest is going to be compounded twice a year, otherwise known as semi-annually. So once you make that last $400 payment, how much is your account going to be worth? Now, again, you're going to be doing this for 10 years, twice a year. That means 200 payments. 200 payments of $400 each. It's going to hopefully, because you're earning interest, you realize it's going to be worth more than $8,000. All right, one of the first important things you need to pay attention to as far as your calculations are concerned, normally when they say, what the interest rate is, that's APR, annual percentage rate. The interest that they're going to pay you every time it's compounded has to then take that annual percentage rate, convert it to a decimal, and divide by the number of times it gets compounded in a year. Interest rate per time period is what they're going to use for the italicized I. So we'll take the 0.08 semi-annually twice a year, divide by 2, and in our formula, we're not going to use 0.08, we're going to use 0.04. So that first payment sits there for 6 months. At the end of that 6 months, then they will calculate the interest and add that in. So that first payment is in the account for 19 time periods and gets interest added to it 19 times. The second one for 18 time periods and so on. So they've got this lovely little chart here. And again, the question asked, how much is the account worth immediately after that last payment is made? Well, you make that last payment, it hasn't been in there long enough to earn any interest. So that's what they're saying here. The last payment receives no interest. So again, if you follow that first payment here on down, 1.04. Okay. Now, hopefully the 0.04, that makes sense. We just talked about that. That's our interest rate that's being added. But where's the 1 coming from? That's right. You get to keep 100% of the money that you had in the account plus another 4%. So that gives us our base there of 1.04. And hey, look at that. We've got an initial amount of 400 times a number raised to a different exponent. This is a geometric series. Now, I'm not sure if this came through very clearly before. If it's an arithmetic sequence, if it's a geometric sequence, that just talks about this infinitely long list of numbers. When they use the term series, that means it's the sum of those numbers. Okay? So we're looking for the final amount of this annuity is the sum of those 20 terms. So put it into our lovely little formula here for a geometric series that we saw before for the final sum. A is 400. Our common ratio 1.04, like I just explained. And there are 20 terms in the series. So, yep, get your calculators. I hope you brought your calculators home. Um, Plug that in, and $11,911.23. So again, all of that interest that got added in there, that amounts to $3,911.23 added into the account. Again, you're depositing $400 times 20 times. That's only 8,000. Only 8,000. Listen to him. The interest then gets added in. Again, it's the power of those exponents because that first $400 kept earning interest time and time and time again throughout this whole 10-year period of time. If you're going to work for only 10 years, man, you got to save a lot more than this. But if you're going to work for 20, 30, maybe 40 years, the power of that exponent is going to make that money grow incredibly. All right, suppose we go the other way. We can use the same idea of an annuity, but reverse the process here. Rather than you taking money and depositing in an account, we change that initial value there of A to be the amount of rent that you're paying. Now, this will apply to not only apartments, but car payments and house payments and all kinds of, anything where you're buying it and then paying it back in regular intervals. Um, all right, so take a look here really quickly with me with our sum, the partial sum of a geometric sequence here. It's where our value here for our common ratio R is 1 plus that interest rate. So 1 minus R to the n over 1 minus R. Now in our denominator, distribute that negative here. The ones will give us a sum of 0, and that becomes negative I. Oh, hold on. That gets kind of tricky if we just have one term and it's a negative. So we do multiply top and bottom by negative 1 so that we don't lose that. So we'll just simply take this that was negative becomes positive, put it in front. This, which was positive, becomes negative, put it in the back. So here's the amount of annuity, final amount here. If you have n number of regular payments where the payment size is R, and be careful there, that script I, interest rate per time period. So yes, in this section, there are several formulas you need to know. If you were to receive $10,000 5 years from now, it'd be worth much less than if you got $10,000 right now. Okay? So reverse that. What smaller amount would you be willing to accept right now instead of waiting the 5 years to get to the full $10,000. So we're looking for what's called present value, or the discounted value. Now, for their example here, they're trying to keep it very simple and keep it consistent with the first example. Suppose we're 8% interest. The one thing they're changing here, compounded quarterly. So hopefully you understand quarterly means split up into 4 parts. 0.08 divided by 4 will give you 0.02. And again, if it's 5 years from now, compounded quarterly, 5 years times 4 times a year, that's 20 time periods. So we know that the present value is $10,000. I'm sorry, the future value, the amount, the final amount would be worth $10,000. What's the present value? 1 plus I to the n. Well, again, we just figured out I was 0.02. We know n, there's 20 time intervals. So now take this equation and manipulate it here. So we'll solve it for present value. Divide both sides by this lovely set of parentheses with the exponent. Just means we're going to take that exponent to the negative power, in the negative 20th in this case. Okay? So then it's calculator time, 10,000 times 1.02 to the negative 20th, $6,729.71. Okay? So again, if you're told what the future value is, or the final amount, you're looking for the present value. Hopefully not too surprising. We're expecting a number less than. So again, here's our lovely little formula for present value. The regular payments, 1 minus 1 plus, again, that time period interest there to the negative n divided by I. It's not you. Sorry, you're not that lucky. Suppose a person wins $10 million from the California lottery. You can choose, and it's the true for the Ohio lottery and just about all of these that are currently being offered. You can take yearly installments for the next 20 years, or you can take a smaller immediate payment. That's significantly discounted, by the way. So that's what we're talking about here, present value. Again, I think just to make the numbers easier, assume we can earn 10% interest compounded annually. So if you're going to get yearly installments for the next 20 years, that means every year they're going to pay you $500,000. So R is 500,000. The interest rate 0.1, and if it's 20 years, N is 20. So again, just plug that into our formula. 50,000, 1 minus 1.1 to the negative 20th. Careful about order of operations there. Divided by 0.1. You could wait, and eventually they'll pay you your $10 million, $500,000 a year for the next 20 years. Or you could agree to accept a single cash payment right now of $4,256,781.86. You buy a house, you buy a car, you buy something where you don't have the money for it right now. The store could offer you financing. By the way, financing on a house is called a mortgage. which for you French scholars, you can verify this for us here. The root word of the word mortgage is death, because it seems like you're going to be paying this mortgage until the day you die. All right, but let's start a little bit smaller than that. Say somebody wants to buy a car. With the job that she has, she can pay, say, $200 a month. She's going to make these payments, get financing for 4 years, interest rate of 12%. What's the purchase price? Okay, so you got to know how much you can afford. We can think of this as an annuity, where the present value is the price of the car. So our value there for I, again, they were taking it easy on you. 12% monthly payments divided by 12. So our value there for I is 0.01. She can make regular payments of 200. So R is 20. Sorry, 200. Sorry. And then monthly payments for 4 years, that's 48 payments. So we substitute into our lovely formula there. The capital R is 200. 1 minus 1.01 to the negative 48th power divided by 0.01. So she can afford a car where the price is $7,594.79. All right, so for the next formula here, basically we're manipulating that last formula there and solving it for R. Okay, so in this case, if you know what the asking price of the car, or I believe the next example here is for a mortgage on a house, figure out what the interest rate is, how many payments you're going to make. We're just using algebra, manipulate that equation, and then solve it for R. Okay, so again, closer look at the formula there. We're going to take interest rate per time period, that's our I, multiply that by the amount that it's presently worth. Okay, so that's usually the amount of the loan or the amount of the mortgage or your college tuition, divided by 1 minus the quantity, 1 plus the interest rate to the negative n. All right, so let's take a look at an example. Suppose we're going to borrow $100,000 for a house, 9% interest as the mortgage loan. Again, monthly payments, 30-year mortgage is fairly typical. Well, at least it was with my generation. Goodness only knows what you guys are going to do. All right, so the present value is the 100,000. That's the amount of the loan. Take the 9%, change that to a decimal, 0.09 divided by 12, the monthly payments. So in our formula, the value for I is 0.0075. And yeah, here's the scary thing when I signed papers for a mortgage with my wife. 12 payments a year times 30 years, 360 payments. How much of a house can these people afford? Well, what are the payments going to be? So again, our value for I, 0.0075, the amount of the loan is $100,000. 1 minus 1.0075 to the negative 360th power. Use parentheses around that entire denominator if you're going to try and do this in one step with your calculator. Big set of parentheses around everything in the denominator. So the monthly payments are going to be $804.62 for the next 30 years of their lives. All right, that's pretty much it. If you look on OneNote, scroll down past this one here, and you'll see the next assignment.